going to talk about magnetic fields. Before we do, I want to talk about some basic ideas behind magnetism. So first of all, a lot of things we'll see in magnetism are similar to electricity. Magnetic fields are similar to electric fields, but you should remember that magnetism is not the same as electricity, and even though there are similarities, they should not be treated the same. To introduce magnets, we're going to talk about a basic bar magnet and a compass, which is just a small bar magnet. So magnetism is a long-range force. That means that it acts over a further distance than other types of basic forces. The long-range forces include gravity, electromagnetic forces, which are magnetic and also electric forces, and weak forces. We have short-range forces. The short-range force that acts over a very short distance is the strong force, and we'll talk about that when we talk about nuclear physics. That's what holds your nucleus together. Magnets have two types of poles, a north and a south pole, and the like poles, so north and north, will repel each other, push each other away, and the unlike poles, north and south, will attract each other. You can tell which type of pole a magnet has if you have a mystery magnet by using either a compass, which has a known north and south pole, or by comparing it to another known magnet. Magnet, like a bar magnet, we know where the south pole is. We see how it reacts to the south pole. That'll tell us the type of pole we're looking at. We also know that materials that are attracted to magnets are called magnetic materials, and they're specific types of materials. Things like paper clips, but not coins. So remember that when we do electricity, we can charge up a rod, say like we could even take a metal pen and make it charged, and anything neutral has an attraction to it. Pieces of paper or anything. Well, this is not true for magnets. Magnetic materials only are attracted to magnets. You'll see no effect if it's something that's not a magnetic material. And also remember, like coins are metals, but not all metals are magnetic. The basic unit of magnetism is a magnetic dipole. A dipole is a north and a south component. Unlike an electric dipole, which we talked about, which had a positive and negative charge, with a positive and negative charge, we could separate the positive charge from the negative charge and treat them completely separately. We cannot separate a magnetic dipole. It has to come as a pair. So we have to have a north pole with every south pole. And if you took a bar magnet and you cut it in half to make it into a north and south pole, your result would be two bar magnets. This south pole would turn into a south and north pole. So you cannot separate north and south poles. So just like we talked about electric fields, we're also going to talk about magnetic fields. Every magnet has a magnetic field in the space around it. We can visualize it with iron filings, and we'll do that in the lab. If another magnet comes into this field, it will feel a force from the first magnet. So magnetic fields lead to magnetic forces, and we'll talk about magnetic forces in a later lesson. So you can remember we had electric dipoles where we had a negative charge and a positive charge that were connected, and when we have an electric field like these red arrows, the electric dipole lines up to go with the electric field. Similarly, a magnet like a small compass needle, if it's in a magnetic field, will line up to go in the same direction as the magnetic field. And you'll notice we called electric field a capital E. Magnetic field is a capital B. That's the symbol we use for a magnetic field. So even though we have this similar property, magnetic fields are not the same as electric fields. Magnetic fields we represent with vectors, and you will see some of the pictures in this lesson use magnetic field lines. We're not going to be using those on the AP2 exam this year, and you will not be drawing them in class, but sometimes they help us visualize magnetic fields. But when you draw magnetic fields, you're going to use vectors, and those are going to be arrows that start from one point and go to the other. This picture also has compasses because we can use a compass to show direction. Magnetic fields will point away from the North Pole and towards the South Pole. That's the general rule that has been established. And also you can see the length of the vector shows the strength of the field. So closer to the pole we have a much larger magnetic field, and further away we have a smaller magnetic field. So the field is the closest right here and right here by the ends of the poles. Now, the Earth, we talk about the magnetic field of the Earth. It has its own field. It is because of the internal dynamo of the planet. And even though we call this the North Pole, it actually, you can imagine that it is similar to a bar magnet with the South Pole pointing close to the geographic North Pole. It's not actually exactly lined up, but it's close enough that we can generally use a compass to find our way. But it's reversed from what most people think. Most people think the North Pole is up here, but it's actually the South Pole, and then the North Pole is down here. The magnetic field of the Earth fluctuates over time, but it's generally slow enough that we can still use our tools for measuring magnetic direction with our compasses. The reason we need the magnetic field of the Earth is that it will block the solar wind that comes from the sun, which would damage the ozone and pull the ozone away, which would allow radiation to get into the planet. So the magnetic field actually serves a purpose in the Earth for protecting us from the solar wind. So besides permanent magnets like a bar magnet and a compass, we also have, we can create a magnetic field from an electric current. So if this is a wire that's going through the paper and I run a electric current through it, what you'll see is that a magnetic field establishes around that wire. This is a straight wire, and its magnetic field will be circular. It'll be concentric with the wire, meaning that the center of the circle will be the center of the wire. And if you could see it from overhead, this is what it would look like. We use this X to say that the current is going into the paper. And you see a magnetic field that is a circle around and a circle around, and we represent it with the vectors. Now you'll notice they're stronger as we're closer to the wire, and as we move away, the field magnitude decreases. This is how you would draw a magnetic field using vectors. I said we're also going to see some magnetic field lines. We won't be drawing these, but this is another way to represent magnetic fields. So if I have a loop wire, that's a wire that makes a complete circular loop. I'm going to get a magnetic field that looks like this. You can see it kind of straightens out in the middle, and it moves in circles around the loops. We'll talk about that more in a later lesson. We're also going to talk more later about solenoids. Solenoids are basically a loop, but then you just keep repeating the loop over and over again, and you can have many, many, many turns in a solenoid. And what it creates is a almost constant magnetic field in the middle, and we use that for certain things in research and also in medicine. So just some notes on visualizing vectors. If you see a circle with an X on it, like you did in the straight wire, that's a current that goes into the page. And if you see a circle with a dot on it, that's a current coming out of the page. You can picture it like an arrow. You're looking at, coming out of the page is looking at the front of the arrow, going into the page is looking at the back of the arrow where the feathers are. Also, anytime we have a vector going into the page, we use X's, and any vectors going out, we use dots. So this would be a picture of a wire that's straight going into the page, and then this is its magnetic field sensed by compasses. So to look at the fields from a current, we're going to look at different types, but for a straight wire, we're going to use a right-hand rule. For that right-hand rule, you're going to take the direction of the current, so we have this wire going straight. You're going to point your right thumb in the direction of the current. And then you're going to curl your hands around the wire in a circular shape. And the curl of your fingers, the direction your fingers curl, shows the direction of the magnetic field lines. So this magnetic field goes this direction. This is how you would know that it goes, in this case, the magnetic field goes counterclockwise. This is how you'd know if it goes counterclockwise or clockwise using the right-hand rule. So here's an example. Let's say we have a current going up. You put your thumb in the direction of the current, curl your hands around, and you'll show a current magnetic field. You can follow the red arrows on the compass. Those are showing the direction of the current. That shows a counterclockwise magnetic field. If your current is going down, you're going to point your thumb downward. So try it right now. Point your thumb downward, curl your fingers around the wire, and your fingers will point in a clockwise direction, which matches the compasses.